Okay. Okay, please scan the QR code if you haven't scanned. And for today's lecture, I will just continue the last session. We are discussing the chapter 8. We still discuss about the heat capacity, if you remember. So I will just show you some of the examples and some examples on how we are going to use uh, some calculation on heat capacity for some conditions. Okay. Okay, I will move to our notes. Okay, so this is uh, the last sections we discussed, 8.3, the change in temperature, and we are developing uh, the delta of internal energy is approximately equal to an integrations from T1 to T2 of the heat capacity, okay, heat capacity at a constant volume, and then dt. And as we may observe from this terminology, that we are going to have, if we are going to have an ideal gas, so the calculations will be exactly as we approximate. And if we have a solid or liquid for the phase, it's still good for the approximations. And for non-ideal gas, it will be valid if the volume is really constant. And usually, most of the time, the assumptions will be it's an ideal gas. So we can also look on what is really happen in uh, when we have T1, T2. So if we take it into two separate, so from A, T1 and V1, perhaps this is typically changed to V2 and then change to T2 and V2, the terminal conditions. And this supposed to be, this change here will be our total of the delta of the internal energy. Okay, I think we can move on. Okay, so this Cv is heat capacity of at constant volume of substance. Okay. All right. Okay, let me move to next sections. Okay. Uh, for quiz, as I mentioned, I will put the link on the Moodle. We have several days, and each question has time limits. Maybe this weekend I will give you, or if not this weekend, then maybe uh, starting from next Monday or Tuesday, you can check the link. Okay? Because I need time for preparing the platform. Now it's I think just 30% the progress for the platform. So please wait for a while. and you can have like several days to work on. You can open your notes to solve the quiz. So I will put the time limit, and the time limit should be enough. It should be enough for you to, if you want to check on your notes. Okay. Okay, let's move to some, I think, example. Let me check the example here. Okay, let me just give you idea on one example here. So we need to calculate here the heat required to rise 200 kilogram of nitrous oxide, or N2O, from 20 Celsius to 150 degrees Celsius in a constant volume vessel. So I believe that's pretty clear and obvious. And we have the Cv, it's given by these equations. Now what we are going to do is we are going to take the integrations from 20 to 150 and put in the equations, and lastly you need to do some integrations. I believe this can be done by calculator. Okay, and I hope you're already familiarized with your calculator. And then the energy balance, we get, this is the, remember what we have here is still specific. Okay, it's a specific internal energy. So what we have, we need to multiply with the mass, okay, or flow, mass flow or mole. Okay, so we need to multiply with mass, so that we have 200 kilogram multiplied with 121 kilojoule per kilogram. So this is the heat that we require, that is required. Okay. Okay, let's move on to give you more. Let me just erase this line and let's put this a little bit outside here. Okay. Now the next is, if we let the delta H, the specific delta H, change in specific enthalpy, resulting from increasing temperature at pressure constant. So we let the T increase for some delta, okay, then we could write a similar approach from what we have in previous sections, that as delta T approach 0, okay, we are going to have the limit, right? And then ratio of the delta H over delta T its approaches a limiting value, which we define this as heat capacity at constant pressure, or Cp. So we define as Cp as limit as delta T going to 0. Okay. Or we could write in terms of Leibniz notations, and make sure that you write P, this terms denotes that it's on the constant pressure. Okay, now from these equations, let me write the equations in the next page. Okay. At least you get the idea first. It's similar approach. The difference is now we have a constant pressure rather than a constant volume. Okay, and from here, the previous one we have the U, right, the internal energy. Now we have the enthalpy. Okay. You could get the idea and imagine that what is the connection between the enthalpy and internal energy. You can remember that this is the connections. So we have the plus the P and V, right? Okay, let me write the, or maybe let me take the equations, make a copy. Okay. Okay, now we let the H is Cp and then dt. Okay. So we let the pressure constant, and T is changing from T to T plus delta T. So from T1 and from T1 to T2 at constant pressure, the delta H will be Cp and dt. And we can construct also the path that we are going to work on. So this is T1 and then P1. So let's say we have P1. We construct that. Imagine that if we change to P2 and then T1, T2 and then P2, and we have this is the delta H. So we may construct two steps, okay, two-step process path, like the delta U that we have in the previous section. This is to show that for whatever we have, okay, if we want to change from some temperature and pressure to another temperature and pressure, we have these conditions. But this condition, of course, the P1 and P2 is the same. It's a constant. Now, of course, the delta H for the first one, the delta H1, is 0 because of the ideal gas. Okay? And the second, or we write maybe about here. So the ideal gas will be 0, and if we have the solid or liquid, this will be if the solid or liquid. So actually, what we have here is the second step. This one, right? Because we have the change only in temperature, right? So we could have the delta H, but since this is going to be 0, we could have this equal to this. Or directly we can write if delta H1 is not 0, then then perhaps this will be equal to, we put P delta P, so the specific volume and delta pressure plus this will be for solid ideal gas, sorry, or non-ideal gas for P constant, and this will be for the solid or liquid. The previous also should be taking the same way. So this is delta U1, delta U2. Okay, this is, it's actually a similar approach. Okay. 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 Now the connections for CP and CP for the heat capacity, we have some relations for obvious reasons. Let me make it smaller. Okay, now, so CP and CP relations. So for liquid and solids, we could say that the value will be a little bit approximately similar. And for ideal gas, where R is the gas constant. Why this is true? Why this is true? If you remember, the Cp is related to the delta U, right? If you remember Cp, it's related to delta H. Without proving anything, you can see that because H is U plus PV, of course, the value for enthalpy will be higher because of the additional P and V. So that's why we can say that it should be added with some constant value, which in this case our gas constant. Okay, I hope very clear here. Okay, you could actually prove this one by one, and you could take the R from the PV and RT and so on and so forth, and you can try to prove that as well. But in case you forget that, is this, we have these two, then of course you can take the CP, the higher one, because of this relations, the enthalpy and internal energy relation. Okay. I hope that makes sense. And for non-ideal gas is not in our discussion, it's not in our topic, so we can skip that for a while. And of course, the heat capacity is mostly in table B2. Okay. Okay. Have you tried some of the question in chapter 7? If they are like the questions that I have given to you like last time. I have several questions. Um, can you try like maybe calculating, um, for example, some questions, how much time you are going to need for solving the question. I hope 15 minutes enough. Okay? I hope 15 minutes. I'm trying to find a way that the question should be maximum having 15 minutes for solving, okay, for finding the solutions. I hope. So that will be the average for questions, for the time limit for the question. Okay, now the we can move to the next section. Next thing. Or do you want to have 35 minutes? Okay. Okay, I think uh, if the question has some guidance, maybe it can be faster, right? Maybe if the question can give you like some guidelines, like you need to find this and this, maybe it can be faster, maybe. But let's try. I will find uh, a questions. Maybe 5 minutes is for. Is it for the question really long? Can you write down which problem set that is? 7 point, which number? I will look and see whether it's true or not. Okay, you can write in the chat box, Ricardo, the number. Okay. Okay. Meanwhile, let me continue a little bit. Okay. Let me just put in some illustration on if you would like to find the heat that must be transferred. Okay. So what we want is there are two cases. Okay. The first case is we have a stream of nitrogen. It has this flow rate, heated from 20 to 100. And then the second one is the nitrogen in a 5-liter flask with the initial pressure 3 bar is cooled down from 90 to 30 degree. So the question is asking the heat that is going to be transferred. Okay. And I hope everyone, you can also check the chapter 7 questions that I just mentioned last time. You could check, and I believe you can mention which number. Okay. It, all the numbers, how, so the total, each questions, how many minutes you need, Rivaldo? Yeah, yeah, okay. So the time, how much time you need for one question? So one question, 35? Is it true? 35 minutes for one question? Okay, I will check those questions. Okay, I will check those questions. If not, then maybe the quiz can be. I will just give you the. I'll just give you the time limit. So you check probably the Moodle, the time that I will announce, and during the times, maybe having just several hours, you need to submit back to me immediately, and it will be just open notes. You can open notes and working on the questions. So that's another option. Another option. But I will try to make it into a platform so that um, immediately you can just click and then work directly. Okay. Okay. Maybe if need more minutes like this, maybe um, that will be the setup for maybe final exam. Final exam. So you can have more relax. You can open notes, but maybe we are doing using the WebEx to open your camera. Okay, just to let you know that you are working by yourself. Okay? Still, you can open notes or even to help you more. I think instead of preparing like your notes, maybe you can prepare like your summary. That will be much easier for you to look on rather than you are preparing your books. It's difficult to find, right, when you move on from the page to page. Difficult. Well, maybe in one page in the A4, my suggestions, much more easier to help you to work on. Okay, okay, back to this ideal gas here, cooling of an ideal gas. So what we have here, what we need, okay, or maybe the first thing that we want to write is the balance equation. So the balance equations, if there's nothing mentioning any small change in energy, for example, the kinetics potentials, I think for now on, we can just ignore all of them. So we just write that or maybe the heat is the change in enthalpy. We can say that because the enthalpy is considered larger than the other part of the energy. So this will be for number one. For number two, we can see that this will be delta U. Because we mentioned, okay, the first one is flowing, right? Flowing. So we could consider this one as open system. Okay, so you need to be careful here. And for the second one, you see that the nitrogen contained in a 5-liter flask, so it's contained in a system. So we could say that this is a closed system. That's why we have the difference in it. This is enthalpy, this is the internal energy. But the way we are looking at the heat is the same Q, same heat transfer. Okay, now for number one, we need to check table B2. We need to check the heat capacity for the nitrogen at pressure 1 atmosphere. So we get the some equation here. We could now find the enthalpy as this is from T1, it's 20 to, what is it? It's 100. And then this is Cp dt. And then solve through calculators, right? And then we could get some number. I believe you just need to plug in your calculator and carefully write the correct equations. Okay, write the correct equations. Usually the CP, it has a long equations with some variables. This will be equal to 2.322 kilojoule per mole. and the flow Q is N and then delta H. So we need to write, this is the flow rate. So we have 233 kilojoule per minute. Okay. So for number 2, so to evaluate the delta U, we need to have the N. Okay, so let me write here. So to evaluate the internal energy, we need to find the N, moles. Okay. Using the ideal gas, PP and RT, right? And then the CP is from CP minus R, right? CP is given as similar to what we have here, and we just need to minus with R, and R we can write is the gas constant, it's the 8.314. We get CP, some equation here, and we get that delta U is from 90 to 30 CP dt, and put on some integrations to calculate the numbers, and you will get this will be equal to negative 1.250 kilojoule per mole, and you get the N is equal PV RT. Okay. So the volume is 5, right? 5 liter. So pressure is 3 bar, 5 liter. This is 8.3. No, not 8. This should be 0.008. 0.08314. Temperature is 363 K. 100 Celsius, right? Or what is this? This Celsius? Or 90. Okay, and then we get the moles is approximately 0.9497 mole. Now from this N, then we could write the Q is N, delta U specific. So we could multiply these two. This will be negative 0.621 kilojoule. You will see that it's the negative signs means that you'll have the heat that is going to be released. Okay, so we have the cooling situation from 90 to 30 degrees Celsius. Okay, another example is when we involving the table B8 and B9. So I hope you have a chance at least looking the table B2 for the heat capacity. Okay, and then there are also another tables we call the table B8 and B9. That is for some substance, okay, that has some combustion reactions. Okay. Combustion reaction. So let me write here the table B8 and B9. They are listing specific enthalpies of species involved in combustion reaction. So we will have air, oxygen, nitrogen, hydrogen, carbon monoxide, carbon dioxide, and the vapor. Okay, now one example from here is okay. I will just show you. There are at least two a particular way that you're going to observe now. So first is we check the table B2 to find the heat capacity, and then we check the specific enthalpies. Okay, there are two ways. Okay, two ways here. This is the first one. This is the second one. Okay. Now we have started. This substance is air. Okay. Of course, it's gas. It's for 30 degrees Celsius. It's going to be still the same substance, and it's cooled down to 100 degrees Celsius. And the energy balance is just the delta H, which is this is the we are going to write down all the this is outlet minus the inlet. Okay, or we could say that this is the delta H specific enthalpy. And then assume ideal gas. Okay, assume ideal gas to simplify our calculations. The first one, we find the table B2, find the CP, right? Find the CP. Delta H is 430 and 100. This is CP dt. Of course, you have as long equations. Okay, I will not write all the equation, but you can imagine should be very long. If you look on the table B2 for air, okay. The second way is the easy one to calculate. So we are going to use the table B8. So the specific enthalpy for air at 100 degrees Celsius, we can use table B9. This is B9. Table B9 and specific enthalpy at 430 degrees Celsius. This is going to be estimated as linear interpolation from 400 degrees Celsius, because I think on the table you have this only 400 degrees Celsius, which is this is 11.35 kilojoule per mole, and you need to interpolate with the 500 degrees Celsius. This is 14.37 kilojoule per mole. So take some interpolation for these two, and you get 430 degrees Celsius. So specific enthalpy for 100 degrees Celsius is 2.19 kilojoule per mole, and for 430, this will be after you take some interpolations, you make linear equations, right? And this will be equal to this 12.17. And sometimes linear interpolations, you need to have aside from this, using that in the chapter 7 also sometimes important when you deal with the steam table. Okay? You can also take sometimes to make interpolation if you have the number like the temperature or the pressure that is in between. Okay? So we have the delta H is 2.19 minus 12.17 is negative 9.98 kilojoule per mole. So we get directly the delta H, and the heat will be N delta H specific. This is, I believe, we just need to take the moles, and then we need to convert all the things here, multiply with 9 kilojoule per mole, and then I would change to kilowatt. So this will be equal to negative 2500. Okay. I think the table B8, B9 will be very, very helpful if you are having like specific numbers for, especially the temperature that is perfectly similar with the given informations. Yeah, and I think you can just do some interpolations for finding the enthalpies, and then you can get the delta of the enthalpies immediately, and then you can use it into equations. Okay. But some cases, if you are not really having these informations, then you need to just do doing these integrations again, and punch your calculator, type in into your calculator, and finally get the results. Okay. And carefully write the equations. Okay. My suggestions. Okay, if you write like a long equation in integral, use bracket to help you draw. So brackets, 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 brackets. Maybe it's just plus brackets, brackets. Okay. So anything you have like a fraction inside, need to do some brackets. Okay. So always use brackets to make a good structure. Okay? I think this is a good way to do it. And not sure if you are uh, trying some writing some programming language. Usually you need to write in a long equation line, right? So you need to be aware of how many brackets you have. Like if you miss out once, you will be not getting your result. So carefully writing your integration in the calculator. Okay, that's my suggestion. Okay, I think we still have another one, estimation of heat capacity. Okay, but would like uh, to move on to, I would like to have just a feedback. Okay, small mini quiz, just to check our understanding, I think. So I hope everyone okay with that. So let me stop this sharing. Or maybe if there are any questions first. If there are any questions. Okay, if not, then let me stop the sharing, and let me give you the other. Okay, can you see the QR code now? Okay, we are playing some games again, and hopefully my question is quite clear. Just designed last night, so I'm not sure if it's still okay. But if there is something wrong, I will let you know. Okay. Okay, please join the feedback. We're just having 5, 6 questions. Really simple. Just choose some multiple choices. Okay, let's start. Okay, and you can write your name or student ID to join. Okay, just for student. Is it for student? Okay, 5. Anyone want to join? Every time you join this, I counted some point for you. Okay, I think we can start. Okay. Anyone else? All right. Let me just start.
Wait, Professor. Wait, Professor. Wait, Professor. It's Chandel. Wait.
Oh, okay.
Wait for
You
me.
can go to the website if you want, the menti.com, and use the code number 87367638.
Yes.
7638. You can go there.
8736 and
7638.
763. Okay.
Yeah. Okay. Okay, I think we can start. Write the name, okay, the name of the equations, if you remember. If not, then you can open your notes. Carefully. Not Bernoulli, it's Bernoulli. Oh, wait. It should be correct. This one should be correct. Sorry. I think I make uh, yeah, it should be Bernoulli. Okay, sorry. Okay, let's say everyone correct, okay? Yeah, I just correct my answer. So Bernoulli, correct. Double L, okay? Okay, another one. Question 2. 3, 2, 1. Let's start to see the question. It should be neither. Do you know why? Because enthalpy state is depend on the initial and the end. So it doesn't matter you choose solid or dash, it should be the same enthalpy. Okay. Okay, next one. Okay. Number 3. Yeah, just a short question. Okay. is false. Okay, it doesn't necessarily to be need to be zero. Okay, do you remember the first law of the conservation should be we cannot destroy or create energy, so it should be the same, not zero, right? Okay, so next question. Okay, okay, still Chantong. Okay, number 4. Okay. Okay, I think that that's true because I believe it's the definitions, right? Based on the definitions. Okay, next one. Okay, everyone got correct. Okay, next one. Question 5. Okay, work done by a pump in a system. Okay, it's false. Done by a system, right? By a system to surroundings, right? Okay. Okay, so let's see. Got correct. Okay, still, Shantom, you win the game. So everyone, hopefully, it's enjoyable and especially remembering some concepts that's pretty important for you. I believe this is the end of our lecture. So see you next Thursday. We will continue chapter 8, and hopefully we can. I believe we can finish chapter 8 Thursday and next Monday, and we can have uh, some some examples and practice. Okay. Yeah. See you. Okay. See you, everyone. You can leave the meetings. Okay. Yeah. You're welcome. Bye. Bye, everyone.